Okay, good afternoon, everyone. Welcome to the session on avatars tracking. We have four exciting talks for you about motion generation, virtual humans, and intelligent avatars. We start with a paper MMG, manipulation-aware holistic human motion generation from sparse tracking signals. You use your own laptop, I assume? Yeah, so just do your plugging in and I just talk until we are done with that, I guess. The presenter is Yilun Cheng from Nanjing University of Posts and Telecommunication. And once you're ready, he will have 15 minutes about to present, and then we have questions. If you have any questions, then feel free to raise them. Some of the student volunteers will go around, will bring you a microphone so you can ask them. For all people online, I will check the Discord towards the end of the talk, so if you have any questions, if it's live streamed, actually, I don't know if it's live streamed. If it is live streamed, then there are people online, ask your questions on the Discord, and I will forward them to the authors. And if one of you have questions, then you can also post them on the Discord, and I'm sure Yilun will then answer them offline. He will probably also be around for the rest of the conference. So again, you will have ample of opportunities to talk with the authors. And with that, please give the presenter a hand, and then we can start.
Thank you for introduction. Our paper is manipulation-aware holistic human motion generation from sparse tracking signals. The motivation of our method is to efficiently synthesize realistic holistic motions from sparse tracking signals in object manipulation scenes. However, naively combining existing specialized body and hand models fails to generate coordinated, plausible, and real-time holistic motions. For example, in the left picture, the method generates obvious body posture errors and object penetrations due to misinterpreting manipulation intent. In the related works, full body motion estimation from sparse signals focuses on using sparse IMUs attached to the body, avoiding complex sensor systems. Kotas et al. In 2017 first employed a statistical body model with 6 SIMU to enhance outdoor motion capture accuracy. Zheng et al. In 2023 utilized constraint-based diffusion, framing sparse to full body tracking as conditional sequence generation. Hand-object interaction post-estimation advances human motion generation by enhancing hand motion in human object manipulation. Sinas et al. In 2016 combined generative and discriminative models for estimation under occlusion and data loss. Zhang et al. In 2021 integrated voxel occupancy with geometric details to regress finger motion from wrist and object trajectories. Tigri et al. In 2024 applied a two-stage inference pipeline to synthesize realistic and temporally consistent bimanual motions. Our work aims to synthesize realistic holistic motion in manipulation-enabled VR scenes, and 3 challenges need to be addressed. The first one is how to compress latent holistic motion space with manipulation constraints to enhance physical plausibility. The second one is how to efficiently extracting manipulation features to regulate holistic motion generation. And the third one is how to improve motion generation model performance and robustness for better VR manipulation experience. Based on these challenges, we proposed our method, Manipulation-Aware Holistic Motion Generation Framework, MMG. The pipeline of MMG includes 3 steps. Step 1 is holistic motion latent learning. Step 2 is initial motion code generation. And step 3 is manipulation-aware holistic motion generation. Step 1 begins by combining holistic human motion data with sparse tracking signals through a cross-attention mechanism. The body and hand encoders then encode these fused features to generate precise motion latent codes for guiding the motion latent code generation in later stages. Finally, the decoder modules reconstruct precise holistic motions using these latent codes. Step 2 aims to generate initial body and hand motion latent codes from real-time sparse tracking signals. We design a serialized diffusion model consisting of a body DDPM and a hand DDPM. Each DDPM contains 5 denoising layers and incorporates time-step embedding T, processed through a multi-layer perceptron. This enables the model to dynamically adapt to different diffusion stages. To ensure feature dimension alignment and information integrity, we implement dedicated embedding modules for 3 input types: a sparse tracking signal embedding module, a noisy body latent code embedding module, and a concatenated embedding module for both the initial body motion and noisy hand latent codes. The initial motion latent codes are generated in 2 steps. First, the sparse tracking signals and a noisy body latent code are embedded in through their respective modules and are concatenated before being put into the body DDPM to generate the initial body motion latent code. Second, this initial body motion latent code is concatenated with the noisy hand latent code for embedding, then combined with the embedded sparse tracking signals as input into the hand DDPM to produce the initial hand motion latent code. Step 3 employs a serialized control network with body and hand control modules, refining the initial body and hand motion latent codes by applying object manipulation representation constraints, producing manipulation-aware motion latent codes. The object manipulation representation consists of the manipulation state label, the SMPL shape feature beta, and the manipulated object feature FO, the manipulated motion feature FDT at the time step T. The manipulation state label indicates whether the user is engaged in manipulation via a control button. We incorporate the body shape feature because local rotations of avatars with different shapes vary for the same manipulation behaviors and sparse tracking signals. The manipulated object feature is represented by polar coordinates. We sampled annual vertex of the interacted object based on the left hand and right hand coordinate systems in order to provide the geometric shapes and spatial positions of the interacted object. We also uniformly sampled ND vertex on both the left and right hands, then calculate the nearest distance to the interacted object surface for each sampled point. This step has 3 sub-steps. In sub-step 1, we concatenated the embedded sparse tracking signals, noisy body latent code, and object manipulation representation features. This combined input enters the body DDPM, a body control module, to generate the residual manipulation-aware body latent code. Adding this residual to the initial body latent code generates the refined manipulation-aware body motion latent code. In sub-step 2, we combine the body motion latent code and noisy hand latent code through concatenated embedding, then merge them with the embedded sparse tracking signals and object manipulation representation features. The hand control module processes these concatenated features to generate hand latent code residuals. Adding these residuals to the initial hand motion latent code generates the manipulation-aware hand motion latent code. In substep 3, we utilized copies of the body and hand motion decoders in the step 1, maintaining fixed parameters without additional training. These decoders use manipulation-aware body and hand motion decoders, motion latent codes to synthesize the final manipulation-aware holistic motion in real time. We compare our results with ground truth, AGIOL plus grip, and SAG plus grip. The ground truth images are sequences from manipulation included holistic motion dataset, GRAB. and they are said to be semi-transparent and overlaid with the results of compared methods. It can be clearly observed that our results are more closer to ground truth than the pseudo methods. This table compares the time consumption at each step. Our method achieves real-time generation in VR, achieving at least 24 frames per second, delivering a 2.62 to 3.55 speed up than other methods. Here, we compare the generation quality. The quantitative results show that our method demonstrates superior accuracy in both the holistic and body motion generation, while maintaining comparable accuracy in hand motion. Our method achieves nearly 40% improvements for holistic motion. In some body-specific metrics, that lead grows to over 50%. We also maintain highly accuracy in hand motion, achieving a 24% improvement. This video illustrates holistic motion generation driven by real-time sparse track signals and manipulation features in a VR scene. Our method produces more accurate and temporally stable holistic motions, maintaining real-time VR frame rates, and achieves a 3.55 speed up over the solar method. In conclusion, we propose a manipulation-aware holistic motion generation framework to synthesize realistic holistic motion in manipulation-enabled VR scenes. A novel object manipulation representation method to extract efficient manipulation features for enhancing holistic motion synthesized accuracy. A progressive manipulation guided training algorithm to improve synthesized quality with reduced model complexity for holistic motion generation. A dedicated user study that proposed for the first time to evaluate the user experience of the generated holistic motion through actual VR manipulation tasks. And there are some limitations of our method. The first limitation of our method is that the hand motions our method generates fail to grip elongated object naturally, instead adopting a pinching posture and may penetrate large model surface. The second limitation is that our method cannot support holistic motion generation for rotational axis manipulations. The third limitation is that our method cannot address the manipulation adaptation problem caused by geometric and physical differences between virtual and real worlds in the realm of human-scene interaction. In the future work, the first possible one is to construct a comprehensive holistic motion data set that incorporates objects with hinge structures and visual sizes. Another possible future work is to study a virtual physical perceptual alignment model for addressing spatial discrepancies between virtual and real environments. Thank you for listening.
Yeah, thank you very much. I just saw that I have a little chair here. Do we have any questions from the audience towards the speaker? If not, then I give you a moment. Maybe you can think about it, because I have a question. You mentioned that the whole system works on sparse input data, but I might have missed it. What is the actual input data for the motion prediction?
It's from the headset and the controller.
So just headset and controller.
Yes, just
Would it still work if I only have the headset, or how far can you reduce the input space?
We haven't tested it, but we trained we have trained the model without we introduced some noise and random dropouts to the model, so it may work and generates the reasonable motions.
Okay, cool. Any more questions? That seems not to be the case, so let's thank the speaker again.
Well, hello everyone. My name is Antoine Mallorca. I'm a PhD student from University of Mons, and I'm glad to present our paper entitled "Robustness of Self-Avatar Animation Beyond Sports Tracking." Um, the self-avatar is the representation of the user within the virtual environment, and its animation is a topic that has been covered quite well since recent years, especially from sparse tracking, so the tracking of headsets, the head-mounted display, and handheld controllers. But this is not a straightforward task because um, to animate the full body of the self-avatar, we only have access to, I mean, the VR consumer grade level devices often come with HMD and handheld controllers, so we only have 3 tracking points to animate the full body of the self-avatar, and we don't have any lower body motion cues. So even recent methods struggles to animate the full body of the self-avatar, especially in the lower body motion, as you can see here on the videos and on the image. So in one nutshell, our approach integrates lower body motion cues from LGB cameras, a setup of multiple LGB cameras, so that can extract motion features on the user in a non-invasive way, sorry. It doesn't need to wear any body sensors, so we avoid the per user calibration step and all of that at lower cost. And our methodology focus on applying pose estimation in each videos, and then applying a triangulation to get a 3D data, 3D Cartesian positions, especially for the lower body limbs, and then combine this data with the tracking of head and hands motion to animate the self-avatar. But this approach raised 2 questions: is how does the accuracy of the 3D joint, of the 3D reconstruction impacts the overall quality of the self-avatar animation? And second, how easily can different pose estimation models can be swapped in your system while maintaining animation quality? In other words, if my self-avatar animation is a deep learning model, and we train the deep learning model with pose estimation models, if I want to use another one, what happens? So what's the outcome of the on the self-avatar animation quality? So first of all, what we did is we use AMS dataset, more specifically 3 subsets that are very common in this task, which is CMU motion capture, the motion capture from BioMotion Lab, and ADM05. And we rendered with 3Mesh library, Python, the motion in 2 virtual cameras we define in the scene. So here we have the video of 2 point of view. Okay. And then we apply pose estimation, several models of pose estimation on these videos. We use the framework of YOLO V8 by Ultralytics, that we use 3 different models with 3 different performance, both in terms of accuracy and in terms of inference time. We use the nano model, the large and the extra large model, and both, as you can see in the bar plot, exhibit different reconstruction performance, while the best is in overall the extra large model and the worst in accuracy, the nano models. Then we process the data, we get the 3D data, right? So what can we do to animate the self-avatar animation? We employ a tweaked version of HMD Poser, which is basically a model that has been designed to get motion features from headsets and hand tracking, and to animate the self-avatar. Here we take advantage of the joint-wise embedding to provide Cartesian positions and confidence score in each cameras. And then the motion data are processed, these embeddings are processed through a spatial temporal encoder, which is basically a LSTM, then a transformer to extract temporal, then spatial motion features, and further estimate the full body pose of the self-avatar. So we trained this model for 40 epochs on the datasets we present on previous slides. Now the results. We report as metric the mean mean rotational error and mean velocity error, but we split the positional errors into upper body error and lower body. And also we report the jitter ratio between the jitter in the the synthesized self-avatar animation and on the ground truth self-avatar motion. First, what we can see is that this approach, even in the presence of noisy data from pose estimation, fast pose estimation, it efficiently tackles the lower pose ambiguity. The VR baseline here is the baseline where we only have tracking from HMD and tracking, and we see that the metric errors significantly decrease in the presence of noisy and occluded 3D data. A more accurate input 3D positions leads to a more accurate self-avatar pose reconstruction, as we got the best results with the YOLO V8X model, which is the larger and more efficient model. But due to the nature of the motion data, the Cartesian positions we introduce in the model, which is quite noisy, quite occluded, we introduce jitter, more jitter with respect to HMD and tracking only, which is a critical situation here. But in overall, what you can observe is that here in the video, the errors are highlighted in red, and the full body pose is especially corrected in the lower body motion on lower body limbs. Then I train my pipeline with my pose estimation system. It's great, but now I just plug in another pose estimation models during inference. So what's the robustness of our approach of this pipeline to a change of pose estimation models? Note that the data with the star means that the error is above HMD and only tracking, which is critical because that means that the incorporating 3D data just does not resolve anything. So on the columns, you have the model is trained on YOLO V8X, YOLO V8L data, and the ground truth 3D positions. And on the rows, you have the model is used YOLO V8X, blah, blah, as inference. So what we can observe is that in certain situation, the incorporating another pose estimation model with another performance drastically reduce the performance of this framework for upper positional errors, and it's even more critical for rotational error and velocity errors. And this discrepancy is somehow proportional to the discrepancy in performance we have in our pose estimation model accuracy of 3D poses. So, to conclude, first of all, if we train our pipeline correctly, the RGB cameras enhance the lower body pose reconstruction in a low-cost way, and using off-the-shelf pose estimation without any retraining. But we introduce jitter effect in comparison with VR only tracking device. Also, this approach is sensitive to 2D pose estimation model. So we need to be very careful when we, for example, a certain condition, lighting condition, or somehow change the need of, we need to get another pose estimation model with more robust performance, blah, blah, blah. We need to be very careful when using this approach. Then we also need subjective evaluation to validate that, because at the end of the story, the user experience is what matters, not technical metrics. Thank you.
Thank you very much for the talk. Do we have any questions that we can ask the author? Yes, there is one. Please, the microphone is coming to you.
Yeah, I was wondering, the jitter, how much impact does it have on the actual user experience?
Yeah, that's why we need further subjective evaluation, because at the end of the story, maybe the jitter affects more the user experience than the mean positional errors. So yeah, that's a very important question, very important topic that we need further investigation. But there are studies that um, already um, highlighted the correlation between the motion misalignment and the sense of urgency of self-avatars and blah, blah, blah. So I think we just need to gather those studies and make them work for for ourselves.
Thank you.
Thank you. Do we have another question? We have time for one more. I have one. You used multi-view geometry as an input, so I guess two camera inputs, right?
Yes.
That sounds to me like you started maybe with one camera in the beginning. Did you try it with one camera input or feed as
But
input?
actually, our use case is what happens if we have quite a large scene. So if the user just go far, um, the 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 field, the field, the range can drastically decrease just with one camera.
Great. Thank you so much. Let's give our speaker another.
Hello everyone. Today I will be presenting our paper, Crafting Dynamic Virtual Activity with Advanced Multimodal Model. On behalf of the Changyang Lee from the Gore-Tex Alpha Labs, I'm Minyoung Kim from George Mason University. Contextually meaningful virtual activity can reshape how we use AR and VR, enabling natural agent behavior, richer experience, better human-robot collaboration, and more dynamic storytelling. Previous approach in human-scene interaction relied on the larger data set and deep generative models. They focused mainly on placing virtual character using low-level geometry and physical constraint, even text-based instructions. But they lacked high-level contextual reasoning about activities and overlooked the dynamic interplay among the multiple characters and their interactions. To overcome this limitation, we need methods that can truly understand semantic context and spatial layout, then connect those clues to human activity and behavior for more realistic interactions. Recent multimodal language models combine linguistic information with visions, giving them a power to interpret scene and character dynamics. By leveraging these strengths, we can generate context-aware, semantically meaningful virtual activities. We propose novel multimodal approach using MLLMs to achieve a deep and detailed interpretation of virtual environment, including object semantics, spatial relationship, and potential affordance. The output is the sequence of the virtual character and virtual activities captured at the distinct keyframes. Our approach has three contributions. First, we use multimodal reasoning with MLLMs to deeply interpret virtual environment. Second, we designed a structured activity representation that guides MLLMs to generate multi-character interaction. And third, we employed an efficient optimization strategy to ensure scalable and natural character placement in virtual scene. Again, our goal is generating contextually realistic multi-characters, human scene interactions. To achieve that, we begin with multi-view scene image for layout reasoning, then pass it through to MLLMs to create virtual activities. Each frames encode pose, positional reference, and detailed interactions. Finally, 3D pose optimization places the character at the optimized place. For visual input, we use setup mark representation. This ensure consistent identification across the different views. We filtered out too small, too far away, outside of field of view, or heavily occluded object. We use this input to enable vision language model to interpret virtual scene. First, we randomly place the camera at different positions. Then, starting with the empty set, we iteratively select the image that covers the great numbers of unseen objects. We feed the multi-view scene image to multimodal model to recognize the scene object, their functionalities, and affordance. Along with multi-view observation, we provide scene area information having a group of scene objects, grouped by distance and visibilities as the textual input. With those two model inputs, our proposed prompting technique layout chain of thought to guide the model to reason the areas of adjacency and to complete the scene graph. Specifically, chain of thought guides the model step by step through its reasoning. The idea is that if the two views show the object from the different area, the model can figure out those areas are close or adjacent. The language model first identify object in the scene, then list the shared object to determine spatial adjacency, and finally build the scene graph to capture the overall structures. Using this interpreted environment context, then we prompted the model to generate virtual activities. Next, we asked the model to fill in the detail what's happening within each keyframe. In this step, the goal is enrich the snapshot for every keyframe T with characters, action, and interactions. This framework describes character using 4 elements. First, the subject, which is the focal character. The language models arbitrarily decides which character will be shown given the scene context. Second, the pose, categorized as a standing, sitting, or lying with more detailed body parameters or animation if needed. Third, the positional reference, which is the anchor the character to some object to clarify layout and activity. And lastly, interaction, define the verb and object or character the subject interact with. Once the activity to show is decided, then next step is where to show them. So we designed the 3D pose optimizer that determine each character's position and rotation to accurately place their 3D position in the scene. Before optimization, we use language model to map text into the constraint. For example, if a father is interacting with his son, the model set rules that they must be within about a meter and they have to look each other. These become the positional and rotational template for the optimization. During the optimization process, we treat engagement of subject as independent activity groups. The optimizer finds the optimal solution by using these positional and rotational relationship of the group. As a result, pose optimization make character look lifelike with their described activities. Then we applied animation clips linked to the interaction verb like talk or sit to bring those interaction to the life. So we showcases 3D animation of generated activity within indoors environment of different types and scales. First result is apartment to show the realistic activity, the generation of our approach. Inside of the apartment, a family shared a moment. The family gather around the table and share their dinner together. And after the dinner, the two kids head to bedroom to play with their toys. The mother take a quick nap and head back to the living room. Meanwhile, the father relaxes for a moment, then begins tidying the tea tables. With the night settling in, the parents relax in the living room, the son has gone to bed, and the daughter freshen up in the bathroom. The next results show the applicability of our approach. In the restaurant, there's a full of diners. Staff move around to serve, and chef check in with the guests for feedbacks. While the staff stay busy attending the tables, some diners wrap up, pay their bill, and exit the scene. The office example highlights our approach to scalability with large-scale setting. At the office, staff are busy at their desk, and some employees head in the lounge area. Employees move around the office, engaging in discussion with colleagues at the desk and the shared space. Later on, the CFO hosts a meeting in the conference room. Additionally, we validate the applicability of our approach to AR scenario to highlight lifelike activity using AR digital twins. To present our effectiveness of our prompting, we conduct a evaluation study. Without explicit spatial reasoning from layout chain of thought, the model often picked the suboptimal distance path, showing the red, rather than the more suitable and nearby routes, highlight in green. Without the visual input, without visual image, the model can pick the wrong object or orientation, leading to unnatural pose, showing the red, while the natural interaction is shown as a green with the visual input. So that's for today. Thanks so much.
Thank you very much for the talk. Any questions from the audience? Yes, please.
Hi, it was a good presentation. Thank you for your presentation. I have a question regarding I think it was where the father and the son has to stand in front of the mirror for the optimization process. So I wanted to know what was the reason behind that they needed to stand in front of the mirror.
In front of, sorry, what?
In front of the mirror.
Uh-huh.
Why did they have to stand in front of the mirror for the optimization?
In front of the mirror?
Yeah, if you could go back to the slides, I can point out which slide it was. Yeah, here.
Yeah.
So in this portion, you said that for optimization, the father and the son.
In front, like they have to be within a 1 meter. Okay. Like they have to be close each other.
Okay.
Yeah.
And why they have to be?
Oh, because they talk to each other. So, of course, the conversation can happen when we are far away. But in this kind of small apartment, the large language model thought that it's going to be more reasoning. When the two people talk each other, they have to be close each other, like standing within a 1 meter. Like, yeah,
Okay, I
that's
see.
why, yeah.
Okay, thank you.
Okay, great. Let's thank our speaker again.
Hi, I'm Victoria. And about 8 years ago, when I was still in my university, I also worked as an e-sport caster. And I could show you some.
手房的那名对。手房的那名队员，他
空了也可以考虑直接跳一个龙。And why? Because it's make money, and I do not have money. And the Chinese University of Hong Kong is very expensive. And actually, I worked very hard at that time because after you like give up your resume, you need lots of rounds of interviews and in-place simulation, and then you could get hired. And after you get hired, you still have a lot of evaluations on your performance, not only on your job performance, but also your popularity, because your commercial value is equal to the work opportunity in the future. And so, to support my job, I still need to do the daily life as a streamer, and also I need to keep updated my social media as a vlogger. And I also need to take part in some formal shooting, to public photo books as a courser, or take the short film and the reality show. And I also need to participate in some offline activity like game expo or fan meeting, and etc. etc. But most importantly, I still need to take time to practice playing the game, and I need to reach the rank above the master. And apart from that, I need to practice dancing and singing an instrument, and I also keep track of my physics and appearance. But actually, I'm still a student in the university, so I still need to keep track of my GPA. And my daily routine at that time is almost like this. And most of time I will think that, oh, if there's anyone could come and help me do my job and I could sleep more. And so I did something. I have an idea. I started a PhD. And the result is that I ended up sleeping the least I ever have in my life. I even don't know whether it's correct or not. But actually, that's why we have this paper. In this paper, we're trying to establish an intelligence enemy avatars based on the VR framework. And it's actually from dialogue agents, but including all the understanding and reasoning and response module. And here we
Vertalk
go.
is capable of
example.
generating smooth and diverse motions that precisely align with the conveyed content. In video, when singing material is provided as input to the workflow, the system produces corresponding vocal output and synchronized movements.
Okay. So here we go through the overview of our working pipeline. That is mainly established by about two parts: the dialogue module and the the animation module. And after your roles profile has been input into the dialogue module, and also including your environment input, and then it will go through a data preprocessing to give crash the noise, and then it comes to the comprehension mode that it will go through a selection between whether it should be explicit mode or implicit mode. And then after it was decided, it will come up the basic response. The medium response will be either user-oriented or the self-oriented. And after the text response has been decided, it will be doing a personal refining to make sure that the final text output by our avatars would keep track with her personality you input. So also auditory speech will be also produced from the text-to-speech mode, and all of these auditory and text result will then come together to the animation module. In the animation module, it's actually a dual source mode where there's a instruction-driven path and also information-driven path. The instruction-driven path will be focused more on your verb. Maybe it will help more with the exaggerated motions. And the information-driven path is mainly focused on the context that you input that decided by the response, because it will help with the harmony motions just slightly with your mouth shape. And then before the motion has actually be synthesis, there's also a conflict solving script to decide whether there is a conflict exists, and if there is, to which should be getting to trash, which should be keep stay. And before the motion has been output, the basic motion would come through to a motion redirection network to make sure that the motion is actually keep track with the enemy style. And since we have a lot of blocks that has been fine-tuning by the LLM, so including the comprehension, the reasoning, and the response. So here goes our system instruction to make this prompt engineering. And finally, here is the animation sequence, would go through the detection script to here shows the details of the process to decide the conflicts. And so after so much complex works, how does this VR talk perform? So we conduct comprehensive experiments on our dialogue module and our animation module. So in the dialogue test, we mainly keep the animation mode fixed and change the dialogue generation network to different kinds of SOTA networks that existed. And in the animation module test, we fix our dialogue mode and only change the animation generation network. And also we conducted the ablation studies to decide the module that we propose is actually really work. So in the dialogue mode, we mainly evaluated the multimodal coordination and the semantic coherence and personality consistency. And in the animation module, we mainly focus on the visual quality and also the motion accuracy. In both of the experiments, we conduct a user test to decide the real engagement feelings when using our VR talk. So here comes the results. This is a table of the comprehensive average evaluation of the dialogue mode and the animation mode. We could see that in both of the experiments, we share the same evaluation matrix on the visual, but the dialogue mode would pay attention to the personality part, and then the animation mode will go through the motion quality. And here we show an example of our motion synthesis results that that make the comparison between different SOTA networks and our VR talk. And we used a unified 1.123 DOR type bridge under the same response. And considering this response, maybe the text is a little bit small, but its main semantic is welcome and the joyful. And we make a a very vivid comparison that the motion of produced by our network will be very fun and very dancing, but the others may be a little bit quiet. And so in the user study, we recruit about 20 participants aged from 18 to 35 to attend, and most of them have both of the VR experience and the knowledge of the anime VTubers, and all of them are from different education and occupation backgrounds. And we take section duration and the interaction rate as our calculation, and there's also a questionnaire included that after you finish watching, you need to like mark your likeness to the section that you watch, and you need to decide which one is your favorite the best. And here goes the statistic result of both of the dialogue and the animation mode. And at the end, we also conduct an unstructured interview. The interviewee was selected randomly from the participants before. And
Quest headset
here
is
is
used to capture the
a
user's voice
reality
and full
example of
body movement.
usage.
Users can also input text through a handheld or USB panel. The Vertalk server processes invite.
And actually, after I figured out that VR talk could work, but I still wondering what it could be done in the future and about my future paper. And then I found out that it actually could work uh, in different applications. That, for example, in the entertainment, she could work as an idol or actor, but in some more seriously fields, she could still work as a therapist or a host. So maybe in the future, we will expand the actual application of our VR talk. And so maybe one day we would really see that she could work as a esport caster in the competition. And I think that's all of my presentation. Thank you very much.
Thank you very much for the presentation. Do we have any questions? Then I will start. You mentioned in the beginning that the motivation for the whole project almost was that you have to work so much and that this might be able to replace you. If you would apply this system for this purpose, how similar would the behavior and the verbal responses and everything of the generated avatar towards yours or any other person? So do you know how similar this would be?
The similarity is actually depends on the document that the personality profile document that you input into these avatars. It actually is depends on yourself. If you choose to make it really similar to the person that you wanna to replace, then you need to put a lot of data to her. But if you do not want it to be too similar, but or you wanted to like create a new personality, that's also fine. Yeah.
Okay, thank you. Any more questions? Yes, there is one all the way in the back. A microphone is being brought to you.
Thank you for the talk. So hearing your presentation, so your contribution is basically for the making animation. That is almost a computer vision based techniques. And so what is the contribution for the ISMAR community?
Sorry, could you repeat your final question?
So this looks like very computer vision paper. So what is the contribution for our ISMAR community?
Actually, recently, the avatars has been applied in test is still stay in the humanity, the real life humanity style. So you hardly see that there's anime style avatars. So we transfer the knowledge domain from the real humanity field to the anime style, and you see in the actually in the like what does it say? The reasoning process. There's a dual source path, and in these two paths, it's different from the now exists process, because in recent process it could only go through a single path that directly transfer what LLM said and to the response of the avatars. But we equip her with this reasoning process, and so that it could decide from two different sources of her motion, of her motion, and it could make her motion more like vivid and not so flat, just according to the mouth shape, but and to keep the harmony, but also the exaggeration that needed in the anime style. Yeah.
Okay, thank you.
Yeah. Thank you.
Let's thank our speaker again. Thank you so much.